let me show what I have uploaded in Edunix first before I will let you. I will give you some time to watch the video. So I have uploaded actually several videos in Edunix, but not all of them are associated with today's class. So let me show you which one it will be used today. Okay. Okay. Where is it? There we go. Okay, so what you're seeing now is the list of lecture videos which have been uploaded by myself, by Pak Hendra and Pak Wawan. And last night I have uploaded these last 3 videos. Okay, so the ones with our course codes. So this would be the 3 videos associated with the current chapter on combustion and boiler systems. Okay, and we are now here in video segment 5.2, boiler energy balance. So what I'm gonna do this morning, because I want to make efficient use of my time as well. Okay, so I will just give you a quick overview of what is in this segment or subsection, if you will, and then I will give you guys some time to watch the video, which is a little bit long. It's about a little over than 15 minutes. So I will give you some ample time to watch it, and then we go back to this class to discuss what you guys have seen in the video. Okay. All right. So what is in store for this boiler energy balance? Let me switch to the presentation. Now, I do apologize if you guys hear some background noise, some background music, because I'm in a public place. Okay. As you can see, this is why I wear my mask. Okay. So sorry about that. Okay, let's see. There you go. All right, so what we do in this subsection is actually giving you guys some basic assumptions and also some basic methodology for the analysis, for the mass and energy balance analysis of boilers. Okay, so today you will study the principles, the basic methods, basic assumptions in the energy balance calculation of boilers. And tomorrow we will discuss one example of how to actually perform mass and energy balance of calculation of boilers, with the ultimate goal actually is to calculate the thermal efficiency or the thermodynamic efficiency of boilers. So really, the one of the most, if not the most important parameter in any boiler design and operation is actually the thermal efficiency of boilers, meaning for each amount of fuel that we input to the boiler, how much energy are we gaining and how much energy is being lost from heat leakages, from inefficiencies in the boilers. Okay, so you can imagine that that is a very important aspect of boiler design and operation. Okay, so just to give you an example, this one is this is a boiler actually in one of the palm oil mills in Kalimantan. So they use a lot of these biomass that they produce from their oil palm plantations and also from CPO production process. And these biomass is actually way in excess of what they require in terms of energy generation. So one oil palm mill, palm oil mill, actually produces more than enough biomass for their own use. So they can afford to run this. This is not a very energy efficient boiler. So as you can see, they have a lot of leakages. They even have fire outside of the boiler. So this is not really a good practice, but they can afford it because they have excess energy, excess fuel. Sorry, not excess energy. But that is not the case for all processes. That is not the case for all chemical processing plants. Not all plants have the luxury of these oil palm mills in Kalimantan or in Sumatra or whatever, that they have so much excess fuel that they can run their boilers actually at low efficiency. So not everyone have the luxury of that. And in fact, most of chemical plants have, they are very concerned about energy conservation because fuel is so precious for them. Okay, so and hence the need for us chemical engineers to be able to evaluate the energy efficiency of boilers is important. Okay? All right, and we will introduce to you this systemic description of a boiler system with all of the input and output flows, and the basic assumptions and basic equations in energy balance. So we have here the BFW. BFW is of course boiler feed water. It has its own enthalpy. This is the fuel, which for which the energy is stated as their lower heating value. Okay. Oh yeah, by the way, most of these analyses are performed on the basis of LHV, okay, lower heating value, for the obvious reason that we do not want to take into account the amount of energy that cannot be used anyway. Okay, so it is always more realistic to perform thermal calculation using LHV instead of HHV. Okay, it will give you a more conservative number, safer number, if you will, because you will end up with lesser amount of energy input to your system. So that will make your analysis safer. Okay, and then we have this product stream. Okay, and then we have blowdown. Blowdown is actually in real life, blowdown flow is typically not continuous, but it's intermittent. Yeah. So it could be on, off for several times in an hour, for example. But this blowdown flow is necessary to prevent accumulation of impurities in the boiler system, okay, which will lead to operational problems if we don't do the blowdown. Okay, and then of course we have the product stream. Okay, sorry, we have recycled steam. So what this means is that in a large chemical processing plant, typically the boiler also reheats, ya, melakukan pemanasan ulang. So the boiler also reheats steam that is being recycled from the process. Okay, all right. Okay, so these are the basic functions of boilers, the basic flows of massive energy. Now, one of the things that I want you guys to be careful with is, oh, sorry, this one here. Let me go back. Okay, so for stack gas, you notice that we do not write the mass flow and the enthalpy and the specific enthalpy for stack gas, because in a typical boiler calculation, this stream stack gas actually represents the total heat losses, if you will. Okay, so here actually we have a combination, we have a summation of the actual heat loss from the stack gas itself, gas teropong, okay, and we have heat losses from radiation from the wall. We have stack gas. We have heat losses from leakages from the insulation and so on. Ya, saya ulangi dalam bahasa Indonesia. Jadi kalau kalian lihat stack gas ini di sini nggak ada tulisannya laju alir masanya berapa dan entalpi spesifiknya berapa. Ini bukannya salah tulis gitu ya, tetapi karena ini mewakili heat losses. Ya, jadi alur yang satu ini sebetulnya mewakili beberapa jenis hilang panas, yaitu termasuk hilang panas dari gas teropong sendiri, hilang panas dari kebocoran insulasi dan sebagainya dan sebagainya. Oke, jadi ini stack gas ini di sini dalam konteks neraca energi, stack gas ini mewakili beberapa moda kehilangan panas. Ya, oke. Then we will review again how to calculate LHV and NHV. Of course, you guys have learned about the Dulong equation. We will use that again and again in the following chapters, particularly in this chapter, of course. We will review how to calculate the combustion air, which include also the excess air. Okay, and we will also introduce to you guys one of the most important control loops. Ya, jadi kami juga akan memperkenalkan salah satu lingkar kendali atau control loop yang sangat penting di dalam teknik kimia, which is air to fuel ratio control, AFR. AFR is a acronym for air to fuel ratio. So in any combustion system, not only boiler, okay, in any combustion system, AFR is a very, very critical parameter. So it is always controlled in a tight manner in the chemical processing plant. And the typical way of controlling that is by using a flow ratio controller. So you can regard this as a quick introduction to process control class. Okay, all right. And that, okay, so this is heating value estimation. You guys have already familiar with this. Excess air calculation. All you have to do is to follow the formulae. But be careful when using formulae in this class. There are different bases that's being used in different equations. Ya, jadi dalam kalian menggunakan rumus-rumus yang ada di kuliah ini, hati-hati ya. Besaran yang harus kalian masukkan itu satuannya apa? Kadang-kadang ada ketidaksamaan antara satu rumus dengan rumus lain. Ada rumus yang pakai fraksi mol, ada yang pakai fraksi massa, ada yang pakai persen. Jadi hati-hati aja ya. Perhatikan keterangan yang terattach pada rumus itu baik-baik. Okay, and remember, theoretical air is never ever sufficient to produce complete combustion. Complete combustion is not equivalent to stoichiometric combustion. Okay. Complete combustion means that all of your fuel are oxidized into carbon dioxide. So zero carbon monoxide. So all of your fuel is combusted into carbon dioxide and water. That's it. Okay, and if you have any other combustible elements in the fuel, it is also being combusted to its most preferred oxidation state. For example, if your fuel contains sulfur, then we assume that the sulfur is oxidized into sulfur dioxide, not sulfur monoxide or sulfur trioxide, but dioxide. If your fuel contains nitrogen, then the nitrogen is at complete combustion, the nitrogen is oxidized into NO2, okay, and so on. Okay, all right. Okay, so there's always an excess air amount that is required to ensure complete combustion. Good. Okay, and then the next one is we're showing you how to estimate excess air. So there are two ways to calculate excess air. One is, of course, if you are being told, okay, you're using this much air, and the theoretical air is this, so you can of course calculate the excess air. Okay, jadi ada dua cara untuk menghitung udara lebihan. Yang pertama adalah kalau kalian dikasih tahu, ya, oke, udara teoretiknya berapa, udara aktualnya berapa, eksesnya berapa, kan itu tinggal dilogikakan saja, ya. Nah, cara yang kedua adalah menghitungnya mundur. Jadi kita memperkirakan, mengestimate. So we estimate the amount of excess air from the flue gas composition. Ya. Jadi kita hitung mundur persentase udara lebihannya dari komposisi gas buang. Ya. To be exact, we calculate the excess air from the mole fractions of oxygen and nitrogen in the flue gas. Jadi dihitung mundur. Ya. Oke, nah buat apa sebetulnya kita menghitung excess air ini? Lagi-lagi ujung-ujungnya adalah untuk melengkapi neraca massa dan neraca energi. Okay, so if you imagine, if you look at the simplified flow diagram like this, so if you don't know how much air is being introduced to your boiler, then you cannot complete this energy balance, right? Okay, so moving on. This is just some formulas, some empirical formula to calculate the amount of flue gas that is being generated for each unit mass flow of fuel. Okay. Now let me give you another example of that you need to be careful with the formula. Here, the letter C doesn't refer to the amount of carbon in the fuel, but it is a conversion factor. So again, please be careful when using this formula, and of course, you guys need to practice quite a lot for this class. Okay, and that is the reason why we include a dedicated subsection only to discuss an example of how to calculate this boiler energy balance. Okay, and that will be done tomorrow. Okay? So because actually this discussion on boiler is supposed to be completed this week, So today we will discuss the basic assumptions in calculation, and tomorrow we will discuss the specific example for the boiler calculation. Okay. All right, and then the next one. This is just if you guys need to convert the basis of flue gas calculation from dry to wet basis. Okay. Remember that moisture in flue gas originates from two sources. Okay. Combustion of hydrogen in the fuel and volatilization of moisture that was there in the beginning in the fuel itself. So some fuel already contain water, not H, okay, not hydrogen molecule, not hydrogen atom, but water. Okay, some fuel contain, well, as you can see from the on the right-hand side picture here, coal, batu bara, frequently contains an appreciable degree of water, moisture. Jadi namanya batu bara itu jangan kalian bayangkan kering gitu ya. Batu bara itu sering kali nyampe di pabrik kalian dalam keadaan basah. Kehujanan lah, kecipratan air laut lah waktu dibawa dari Kalimantan ke Jawa gitu ya. Jadi bahan bakarnya sendiri sudah mengandung air. Okay. So again, air di dalam flue gas, dalam gas teropong itu berasal dari dua sumber, yaitu dari oksidasi hidrogen, atom hidrogen di dalam bahan bakar, dan dari penguapan air yang memang dari awalnya sudah ada di dalam bahan bakar itu. Okay, so I think that's pretty clear. Okay, and then we're moving on to calculation of boiler efficiency and heat losses. This one in particular, this one is called a Sancti diagram. Okay, a Sancti diagram is a pretty useful tool for energy analysis. Basically, it tells you how much or the types and the amount of energy transitions in a system. Okay, so pay close attention to what the Sankey diagram is, make sure that you understand what it means and how to draw it. So, for example, the width of the arrow here represents the magnitude of heat flow. So there's a reason why this arrow is small, because the heat flow is much slower than this one, for example. Okay, so this is the incoming energy. Okay, so this is energy in, and this is the energy conversion steps, and this is the produced energy. Okay, energy transfer to the next stage, and energy lost to the environment, and so on. Okay, so it's pretty easy to understand as long as you pay close attention to it and you review it again and again. Don't just look at it once and somehow you convince yourself that you understand what the Sankey diagram is. Okay, I have in the past. Okay, I have in the past make an exam problem out of this Sankey diagram, and almost none of my students were able to answer it. Okay, I think not. So the problem is that the students didn't really have pay enough attention to what Sankey diagram is and what it tells us. It's pretty straightforward. Okay. Okay, in the last few slides, we discuss about the types of heat losses in boilers. Okay, major types of heat losses in boilers. Okay, that is what it's called a dry gas loss, or DGL, which is one of the most important type of major heat loss. We have moisture loss, MCAL, or moisture combustion air loss, incomplete combustion loss, uncombusted carbon loss, and so on. And we will discuss, we will close this subsection, this video segment, with a quick note on what are the most important types of heat losses in actual boilers. Okay. Now I will give you some time to watch the video. I'll actually give you 20 minutes, so we will meet again at 8:40. Okay. So watch the video, and we'll be back here at 8:40. Okay, and yeah, don't quit the meeting room. You can just watch it and remain in the Zoom room, okay? As I will. All right, and we'll discuss at 8:40. Okay, go ahead and see the video. Only video segment 5.2. Do not watch 5.1 or 5.3. You'll just, for now, it's only segment 5.2. It's already in the internet. Okay, go ahead. Okay, so it's now 8:40. Any questions or comments from you guys?
Sir, so I'm not done with the recording, but I've reached to the part where we have a homework.
What?
I've
Oh,
reached,
you mean in the video?
yes.
In you mean in my video?
Sorry, sir.
Yeah. If your voice is breaking up, Tamaria.
Before I was using the
Uh,
speaker. Yeah.
yeah. If you guys have if there's any, I forgot what I posted. That video was from last year. But anyway, if you guys see any homework in the video, just skip it. Just ignore it for now.
All right, great. Thank you, sir.
Yeah, we'll discuss homeworks tomorrow. Any other question? That homework is old anyway, so we have to change it anyway.
Sir, I want to answer. It's actually regarding the in the formulas there are like CO, CO2. Like, is that percentage or is it like mass fraction or something, sir?
Hang on a second, let me pull up the PowerPoint. So you can tell me which formula that you're talking about. Okay, so this one? No?
That's one of them, sir. Yeah.
Sorry, I think my internet connection here is actually not that good. So can you repeat, Kevin? Is this the formula that you asked me about?
Yes, sir. That's one of them, sir.
Yep. Okay. Right. So this is composition, and you see there's a number 28. That's not X, by the way. Okay, that's a 28 multiplied by CO. So 28 is the molecular weight of carbon monoxide, right? It's 12 and 16. Yeah, that's 28 is a. So that number must be in. That must be in mole fraction, I think. Pak Hendra, can you help me to check the formula? I think my judgment tells me that it's the CO and the CO2 and N2, those are all in mole fractions. But if you can kindly check this and inform the class tomorrow, okay?
I will double check.
Yep, thank you. Pak Hendra, I think this is, I'm pretty sure this was taken from Pak Heri's diktat. So you might want to start there.
Okay, Pak.
And also you guys, the students can also check. So I think you've already been given the Pak Heri's diktat, although it's in Indonesian, I believe. But please do check in that diktat because I'm pretty sure this formula was taken from there. My guess, okay, my initial guess is this is in mole fractions, but please make sure. Okay, any other questions?
Mika, I have checked that it's correct from mole fractions, but
Mole fraction, okay, thank you. Yep, so yeah, it is confirmed. It's in mole fractions. You can sort of guess, okay, because there's a number here, okay, 28 and 44. So these are all molecular weights, right? And yet the end result is given in mass unit. So this is must be conversion from mole to mass. Okay. Okay. Any other question? If not, we will see how we use these calculations, this formula, tomorrow when we discuss example. So, and actually, you can, of course, it's recommended. It's highly recommendable if you read it in advance. So tomorrow we will continue to part 4 in this module, which is the example problem of boiler efficiency evaluation or calculation. Okay. So we will learn about how to implement the formulae to calculate the different types of heat losses, and also how to complete the mass and energy balance, and ultimately, okay, ultimately to calculate. Where is it? I'm trying to be dramatic here, but I. Anyway, geez. Anyway. Okay, so this is what we're aiming for, okay, the thermal efficiency. So for each amount of energy or fuel being introduced to the boiler, how much energy that we gain in the steam, okay, and how much energy is being lost through the system as dry gas loss, as moisture loss, unburned carbon. Here you can clearly see, okay, on the right hand photo here, of course, you see that the smoke is black, right? It's like, you know, seperti tinta cumi, okay. So this is a sure way to tell us that this combustion system emits a lot of unburned carbon, because if it's complete combustion, it's not supposed to be black like this, okay. Black means you have soot, okay. Kalau asap pembakaran itu warnanya hitam, itu artinya di dalamnya terkandung partikel aerosol jelaga, aerosol karbon. Ya, jadi ada partikel-partikel halus sekali yang berupa karbon. Ya jelas itu merupakan unburned carbon kan ya. Begitu warnanya hitam artinya pembakarannya pasti tidak sempurna. Itu sudah bisa dipastikan. Ya, pasti banget gitu ya. Jadi udah jelas ini boilernya adalah boiler yang efisiensinya rendah. And as I mentioned to you at the beginning of this class today, a lot of these boilers, these palm oil mills in Indonesia, they don't really care about heat efficiency because they have an enormous amount of excess fuel in the form of biomass. Ya, jadi kalau dikatakan krisis energi apa ya tergantung tempatnya ya sebetulnya ya. Kalau kita bicaranya pabrik-pabrik sawit yang ada di dekat kebun sawit, semua itu mempunyai ekses energi luar biasa karena mereka menghasilkan biomass dalam kuantitas yang luar biasa besar, berlebih-lebih sekali untuk mereka, ya. So just a closing note, we recognize 3 types of biomass when it comes to palm oil palm. Sorry, I keep comparing between palm oil and oil palm. So oil palm is the plant, palm oil is the product. So there are 3 types of oil palm biomass. Okay, there's the empty fruit bunch, tandan kosong. Okay, there's the mesocarp fiber, jadi sabut kelapa sawit yang sudah diperas minyaknya, and then there's the shell, okay, the palm kernel shell, PKS, okay, palm kernel shell. Jadi inti sawit, ya. Jadi kalau di kelapa besar ya, kelapa yang biasa kita makan sehari-hari, itu adalah batoknya, ya. Jadi batoknya kelapa sawit itu adalah shell tadi, ya, cangkang sawit. Okay. In Indonesia we call it cangkang sawit, and then the fiber serabutnya itu namanya adalah mesocarp fiber, MF. Okay. And then we have the tandan kosong, okay, the empty fruit bunch. So what CPO plants in Indonesia consume are the shell and the fiber. They don't typically combust the fruit bunch because they contain a lot of potassium. Ya, jadi tandan kosong sawit ini biasanya nggak dibakar karena dia mengandung kadar kalium yang sangat tinggi. Nah, kadar kalium yang sangat tinggi ini menyebabkan abu dari tandan kosong sawit itu mudah meleleh di dalam boiler. Okay. as fusion temperature is so low for empty fruit punch, and they have excess amount of palm kernel shell and mesocarp fiber anyway. So, and they typically they're even able to export these excess biomasses. Okay, and because the empty fruit bunch is troublesome, they usually just return it back to the plantation as a mulching material. Okay, so that's the situation of energy supply in palm oil plantation. Okay, so they have excess amount of energy for their own use. Ya, tapi seperti yang saya sampaikan lagi, sangat sedikit industri kimia yang memiliki ekses bahan bakar seperti pabrik sawit. Kebanyakan pabrik kimia itu merasa bahan bakar itu adalah sesuatu yang precious, sesuatu yang harus digunakan sehemat mungkin. Okay. Alright, thank you very much, and we will see you tomorrow if there isn't any other question. Okay. Okay. No. All right. Thank you very much. We'll see you tomorrow afternoon. Okay. Stay safe. Stay healthy, guys. As always.